Hello, so we're into Unit 8. In Unit 8, we're going to get more into derivation strategies and start doing symbolizations with our Chapter 2 symbols. In this video 8a, I'm going to discuss some basic derivation strategies. As with the previous derivation system, we'll see that it's going to take a little while to learn the basic derivation strategies, although it's going to be easier still because you're not having to learn the system at the same time. You're learning new inference rules and new strategies associated with them, but you're not learning a whole system. So, okay, let's just briefly review our new rules. So remember that we have introduction rules. So one example of an introduction rule is the rule addition, and it's an introduction rule for the disjunction. It says if you have Q, you can infer P or Q. If you have P, you can infer P or Q. We call it an introduction rule because we're going from a less complex formula to a more complex formula, and one in which it's the introduction rule for disjunction because the more complex formula has a disjunction in it, whereas the premises might not. The elimination rule for the disjunction is MTP, and it says if you have a disjunction and you have the negation of either disjunct, you can infer the other disjunct. So if you have not P, you can infer Q if you also have P or Q. For the conjunction, we have one introduction rule, adjunction or ADJ. It says if you have both conjuncts, you can infer the conjunction. We have two elimination rules, simplification. If you have the conjunction, you can infer either conjunct, and you can infer both of them, in fact, just in two different steps. For the biconditional, we have the rule CB, which says that if you have the conditional in both directions, you can infer the biconditional. And we have the rule BC, which says if you have the biconditional, you can infer either or both serially of the conditionals. So those are the new rules. I say primitive because we're going to be talking more about derived rules as we proceed. The primitive rules are the ones that are defined to be part of the system, and we'll see that there are others that aren't defined as part of the system, which we'll talk about later. So we're going to have to work on strategies in a couple of different ways. First of all, we're going to have strategies for showing our different kinds of new sentences. So we're going to have strategies for showing conjunctions, biconditionals, and disjunctions. We're also going to have new inference rule strategies, and we're going to have strategies for new unused sentences. So just as we had strategies if you had a negated conditional in Chapter 1, or you had a conditional you hadn't done modus ponens or modus tollens with. So similarly, we'll have strategies for what to do if you have, a disjunction that you haven't used, or the negation of a conjunction that you haven't used, and so on. And in particular, one important thing will be for with unused sentences, what to do if you have an unused disjunction. And we'll also be talking about derived rules. In this video, in this unit, it's mostly going to be the first two groups, so strategies for showing new sentences and inference rule strategies. I'll talk a little bit about one important derived rule at the end of this video. So what if you want to show a conjunction? Well, if you might think I'll do assume indirect, but then you just have not, box, and circle, and what would that do for you? Well, it wouldn't do anything for you. You could say show unnegative, but then you'd just be showing the conjunction again, and we don't have a rule that applies to negated conjunctions, so just assuming ID won't work. So instead, what we want to do is we're going to take advantage of our introduction rules. And so, but we're going to work up to that. So the first thing we're going to do is we're going to do a subderivation of the left conjunct. And so we'll proceed along. However we proceed along, we'll make an assumption that's appropriate to the whatever it is we're trying to show. And then eventually we'll succeed in showing it. And then we'll go ahead and we'll show the right conjunct. And again, we'll make an assumption that's appropriate to it. And we'll proceed along, and eventually we'll get it. And then and this is sort of the novel thing, we're going to say, okay, we're going to use our introduction rule for the conjunction, and that rule is adjunction, and it says if you have both the conjuncts, you can infer the conjunction, which is what we do here. But now note that we have a direct derivation of the conjunction, and so we can say direct derivation and box and cancel the whole thing. So the strategy to showing a conjunction is to show both of the conjuncts. And if you look in the program, you'll see that there's actually a show command for that called show conj for show conjunct. What about if you have a biconditional? Well, it's basically the same thing, because we can think of a biconditional as a conjunction of if box then circle, and if circle then box. So first we'll show one of those, And in this case, we know what the assumption is going to be. It's a conditional assumption. But then, we'll go ahead and proceed as we normally would, and eventually we'll complete that derivation, that subderivation. Then we'll go ahead and we'll show the other conditional, and we'll proceed as however we would, and eventually we'll succeed in showing it. So then we'll have both the conditionals. Once we have both the conditionals, we'll apply the introduction rule for the biconditional CB, which lets us infer the biconditional. Once we have that on line 10, we're done. That's a direct derivation. So that's the second, so that's how we show a biconditional. Okay, well, what if we want to show a disjunction? This setup is slightly more complicated. So we'll start with show the disjunction, and then we'll make an indirect assumption. Now, we don't have any rules that apply to this, and we're not going to do show on neg, because that would just be to repeat the first show line. But we'll see, we're going to use it in a little bit. So the first thing we're going to do is we're going to try to show one of the disjuncts. And here I've set out to show the left disjunct. It doesn't actually matter which one you start with. And you'll proceed, and at some point you'll get stuck, and you won't be able to go forward. So then you'll show the other disjunct inside of the subderivation of the first disjunct. And that will proceed, and at some point you'll be able to complete that subderivation. Now, you should be making assumptions both off of lines 3 and 6, but what those assumptions will be will depend upon what the box and the circle are. So anyway, you get the circle, and then you can say, okay, from the circle you can infer the disjunction. Now, you might think, oh, I'll do direct derivation, but that won't work because you're still trying this, the subderivation, the show line we're working on is a subderivation. It's line 3 still, and that's, so we don't have a direct derivation of box. We have a direct derivation of box or circle. We have box or circle, and if we were working on line 1, then we would have a direct derivation of line 1, but we don't. What we do, though, have is on line 2, we have the negation of box or circle, and so we can repeat that down, and then we have an indirect derivation. And that completes the subderivation of square or box, and then we can use addition again to get box or circle, and then we have a direct derivation. So this is slightly complicated. You first assume the negation of the disjunction, you try to show one, you proceed along however you would, making the appropriate assumption. At some point you will get stuck, and then you try to show the other disjunct, and you'll again make an assumption and proceed along, and at some point that will succeed. Once that succeeds and you've got circle, you can say, okay, from circle I can get square or circle. I can copy down my indirect assumption for an indirect derivation. That will give me square, and from square I can infer the disjunction. So it's a little bit more involved, just because of how disjunctions work. So those are the show strategies. We want to also remember our inference rule strategies. So we want to be looking to apply elimination rules. For the conditional, for the arrow, that's MT and MP. For the conjunction, that's simplification. For the disjunction, that's MTP. And for the biconditional, that's BC. We want to apply the introduction rules when doing so will help. So MC is our, it's a derived rule for the arrow. Adjunction, addition, and CB are the introduction rules for the conjunction, disjunction, or biconditional. How would it help to apply an introduction rule? Well, in two ways. It might help because it would give us something that would box and cancel, and indeed that's what we saw in each of the three strategies. In those three strategies, we get what we're trying to derive by using the appropriate introduction rule, right? If we're trying to show a conjunction, then we show each of the conjuncts and then apply adjunction, the introduction rule. And so there are other situations where it might help to, where you might realize, oh, if I apply the introduction rule, it will help me box and cancel. The other thing is it might help us to apply an elimination rule. So if you have a conjunction, you have a conditional, if P and Q then R, and you have P, and you also have on another line Q. Well, if you apply addition, you can put P and adjunction, you can put P and Q together to form P and Q, the conjunction, which is the antecedent of the conditional, if P and Q then R, at which point you can apply modus ponens. So that's an example of how you might use the introduction rules to facilitate an elimination rule application. So I want to talk before this is sort of the last main topic of this video, and then I'm going to summarize it. I want to talk about one important derived rule. So we'll get to the rule in a second. So suppose you have the negation of P and Q. that's equivalent to not P or not Q. If the negation is false, then at least one. What does that mean? It means it's not the case that both P and Q are true, and that could be true if not P is true, or it could be true if not Q is true. It could be true if they're both false. So, or if both P and Q are false. So these are equivalent. And similarly, not P or Q, that's equivalent to not P and not Q. So what we have here is a sort of a negation distribution. It's telling us if you have a negation over a conjunction or disjunction, here's how to move it inside. Or here's how to move it. If you have inside of a conjunction or disjunction negations, here's how to move the negations out. And you just move the negations in or out and flip the sign from a wedge to a V. So there are theorems. There's theorems associated with these equivalences, and they give us, so theorem 65 will give us these two rules if we derive it. It will give us not P and Q, therefore not P or not Q, and will also give us not P or not Q, therefore not P and Q. And then there's theorem 66, which is the other version. It says if you have not P or Q, then you can infer not P and not Q, or if you have not P and not Q, you can infer not P or Q. Now, theorem 66 in particular, this version, the not P or Q, therefore not P and not Q, is quite useful if you're trying to show a disjunction. Because you can go through that strategy we saw before, or you could do this. You could say show box or circle, assume ID not box or circle, and then apply De Morgan's, and you have not box and not circle. And that you can simplify to get not box and not circle. And that's easier to do than going through that somewhat more involved structure that I talked about a few slides back. So theorem 66 is a good theorem to derive. This is useful, theorem 65, because you can use it instead of showing a negation on not P and Q. It's not very helpful for showing conjunctions, but if you have the negation of a conjunction, you can use it to move the negation inside, and then you have to figure out how to use not P or not Q, but that can be done. So here are the two theorems and their associated rules. So if you want to enable these rules, then you need to go and derive the associated theorems. And they're going to be theorem, they're problems in the derivation module. Actually, let's just hop over there real quickly. So let's see, that's the symbolization module. We want to be here in the derivation module. So if we click select, then we get the problems. And theorems, oh, they actually start low down. Okay, so they're just numbered. That's funny. I'm surprised by that. Okay, well, so yeah. So, but here we go. So the theorems start at 24. So the De Morgan's rules, the theorems that will enable them are 65 and 66. And 66 is the particularly useful one. So if you do this problem, then you can use the derived De Morgan's rules. And if you're not sure about how that works, take a look at the previous video, I think in Unit 6, on theorems and derived rules. Okay, so to summarize our initial strategy comments, we know there's a setup phase, and it's always going to start with show conclusion. And then if you're trying to show a conditional, that's chapter 1 strategy. You go through the assume CD, show consequent, assume whatever, and then if you're trying to show another conditional, keep going until you're not trying to show a conditional anymore. If you're trying to show a conjunction, first show one conjunct, then show the other conjunct. If you're trying to show a conditional, if you're trying to show a biconditional, first show one conditional, then show the other conditional. And if you're trying to show a disjunction, then either go derive theorem 66 and then do assume ID plus De Morgan's, or do that the strategy I talked about some slides back, where you show one disjunction and then inside of that you try to show the other disjunct. You'll need to use that strategy to get the theorem 66. So you're going to have to use it at least once, but if you derive theorem 66, then you won't have to use it again. So once you've through the setup phase, then you look for inference rule applications, and as I said, main thing is looking for elimination rules, but also if you want to use the introduction rules, if they will help you with elimination rules or boxing and canceling. And then they're the standard subderivation strategies, and there are going to be new ones that we'll be getting into specific situations, and they're basically just natural extensions of the ones we've talked about. So I'll be talking about those in further videos. So I'm going to record another video or another couple of videos doing some demonstration derivations in the module that will show how we apply these strategies. And then there will also be some symbolization videos. So remember, when you're trying to do subderivations, do ones that will help you with the derivation that will interact with unused lines.